Well, my name is Torsten Hoefler. I'm here at ETH Zurich in Zurich in Switzerland. So we are essentially right here winding up, or we have been winding up the PASC15 Conference. And I'm going to talk to Satoshi Matsuoka from Tokyo Tech, or Tokyo Institute of Technology, a little bit about the conference to find out his impressions. So he has been here the whole time, sitting through lots of mini symposia and talks. And so Satoshi, what have you learned?
Well, I think I learned various aspects of these multidisciplinary research in high-performance computing that's going on, especially my being a systems researcher. I learned a lot about the needs of the applications and what are the scientific results that they're pursuing as we scale to exascale and beyond. So it was a very enlightening conference for me.
So yes, you're hitting on one of the main features of the PASC conference. It is this very interdisciplinary mix around scientific computing, which also a core HPC component, which is very close to my heart and yours. So what did you learn about these applications? Can you give a particular example of what will influence our research?
Well, for example, I learned about a lot of the characteristics that are required in terms of, for example, latency, bandwidth requirements, and also what are the programming models and some of the difficulties that people are facing with in terms of scaling these applications to massive scale. Certainly these applications are very complex, and certainly these applications will require a lot of assist as the hardware and the underlying architecture and also the software layers will become more complicated as we try to cope with the actual complexity of the application. So, I think we learned. It's hard to pinpoint which aspect I learned that were most prominent, because many of these, in some sense, we have known already. But many of these were exemplified. For example, in Jackie Chen's talk this morning, there were a lot about not just with the there were mentions of what are the architectural advances that can be made to speed up the application? And some of the architectural innovations could really scale up the application by a factor of 4, which is quite significant when you consider you're building either a 20 megawatt machine or an 80 megawatt machine for exascale. And also, we learned some of the difficulties with respect to programming models, the difficulties they're encountering in these multi-physics simulations, in that they really have to try to orchestrate the tasks that are actually generated from the multiple components of the multi-physics applications that are going on, which are no longer not necessarily bulk synchronous, but you have all these interacting pieces. So they're much more like component-based programming that we see in mainstream in computer science or industry type of or like business type of applications. But of course the difference is that we have much higher expectations and performance. So somehow we have to bridge the gap between these highly flexible software, like component task parallel stuff that's been studied for years, but we have to really apply it in high performance in very complex heterogeneous machines. So, and I can go on, but there are many things I learned with respect to these requirements.
So just to pick on one particular topic. So I've seen you in the session FPGAs for scientific computing. It was a very interesting session, I think. So what do you think? Should we co-design architectures in the sense of FPGAs and runtime systems? Or do we have to do that to reach the next gap or to bridge the next gap? Or what do you think?
Well, so it depends on what you regard as the trajectory over the next 4 or 5 years, or if you're considering like 10 years. So it is true that as we scale to higher scale with many cores, of course, many cores is a very effective technology. We see this in GPUs. This is like Xeon Phi, and this has certainly enabled us to scale to much higher performance due to exploiting the principle of slow and parallel. But then this largely boils down to restricting the application being more or less weak scaling. And of course, we can circumvent some of that by having a heterogeneous architecture, and that's what we see in many of the GPU architecture. Unfortunately, Intel hasn't quite adopted that yet, but eventually I believe they will. But then there will be, will there be applications that even with this heterogeneous, highly parallel, slow parallel cores, plus that is throughput cores, and then you have the latency tolerant cores, But are there applications that are even restricted then, even with these types of configurations? And we're starting to see some of these, especially in the area of applications where the strong scaling latency is becoming even more prevalent. And for example, in the Anton, you have the Anton very specialized architects for accelerating molecular dynamics. But it took a lot of effort to build Anton. Can we actually make that more general by using FPGAs? And are there classes of application that can exploit that? I think that's a big question, but as we move forward, I think these more and more of these applications become more prominent as we, because of the Amdahl's law. And efforts to use customization to push the envelope of application portfolios for high-performance computing will become more important. So, and use of FPGA in general is one method to try to achieve that goal. Yeah.
Excellent. So what are you concretely planning to do, let's say, until next year? So what are the next steps? Yes.
The next steps. So the other thing, the aspect that was covered in this conference is big data. So and also things of resilience, and we have projects on those. So we'll certainly try to push the envelope in those. For example, in big data, our projects is trying to converge the HPC technologies with traditional big data. So we have a series of work doing that, both in terms of the ability to handle big data, and also in terms of accelerating big data algorithms like deep learning. So deep learning. So we have some hands on that. Resilience as well. How do we scale to billion scale machines? What's the effective algorithm? In fact, I have a theory that soft errors may not matter, but there's a long story, so I'll skip that. So that's sort of a near-term research goal. And long-term, our concern is what will happen after EXA. Is there a life after EXA? Is there a life after Moore's law ends? And I think over the next year we'll try to initiate this long-range research, which may span more than 10 years because Moore's law will probably end beyond 10 years. So we still may have 10 years life left, but we have to start research now in order to anticipate what's going to happen and really cope with the time when Moore's law ends, and we'll probably work towards initiating that. And hopefully you can work with us, Torsten. And I know you're very interested in the subject.
Thank you very much. So with that, I want to mention that we will have another PASC conference next year, 2016, in Lausanne, not Zurich, and we hope to see you there, Satoshi. And thank you very much for the interview. And
thank you.
See you in Lausanne.
Yes, definitely.
Bye.
Yes.